Greetings, sir. I hope you are feeling well. We are from Team 10, so we will talking about the variable state of vein, the VSV control system for the Mitsubishi M501J gas turbine. So, going to the presentation, I would like to introduce my team that will come. The Mitsubishi is one of the high efficient gas turbine widely used in the power plants. So, one of the most important components of this, like a gas turbine, is the variable state turbine, or we can call them VSV system. So, the VSV controls the airflow entering the compressor by adjusting the angle of the guide valves. So this helps to improve the efficiency, maintain a stable operation, and prevent a compressor store under different operation conditions. So because of this critical role, the vane position must be controlled accurately and respond quickly to the change in the turbine position. So this slide shows a closed loop control system of the VSV. So first we can see the desired vane position that is given as the our input, and the controllers compares the desired position with the actual position measured by a sensor. So it will calculate the error and sends a signal to the hydraulic actuator, which will adjust the vane angle. So this feedback will process continuous repeat to ensure like accurately position and a stable turbine performance. So as we talking in the first minutes of our introduction, the Mitsubishi M501J is the high efficient primary movement, like a combined cycle power generation. So we need to control them. So beside our background, we need to create a problem statement. So this system is essential because it's control the airflow entering the compressor, which directly affect the turbine efficiency and safety. So, however, we need to achieve it like a precise control. So this is will be a challenge for us. So the vane angle must remain with its operation range while keeping the overshot below 5% and achieve a response time of less than zero point 0.8 seconds. So, in addition, the hydraulic actuator must produce enough force to move the vanes reliability during the operational time. So, to address this challenge, our project has like four main objectives. The first one is the development a mathematical model of the VSV actuator and control system. The second one is to design a suitable controller for accurate positioning, and the third one is to simulate the system using the MATLAB and Simulink. Finally, to evaluate the controller performance using parameters such as rest time, setting time, overshot, and the state error. And for our scope of our project, we focus on modeling the VSV system, designing the control, performing like simulations, and analyzing its performance. Hardware implementation and mechanical modification and testings on the actual Mitsubishi M501J gas turbine are beyond the scope of this study. So our work is there limited to simulator based controller development and performance evaluation. So
Hello and Assalamualaikum. My name is Amri by Pengeran. I would like to present to you our Group 10 literature review. So without further ado, let's go straight to the point. Um, so first and foremost, for the gas turbine variable geometry systems, literature shows that modern gas turbine use variable geometry systems, which include variable inlet guide vanes, variable stator vanes, and bleed valves. Among these, variable stator vanes play a critical role in controlling airflow and preventing compressor surge. Studies indicate that VSVs help maintain compressor efficiency during part load operation and transient conditions. Most industrial gas turbines use hydraulic actuators because they provide high force output and fast response, making them suitable for accurate vane positioning. So next is that this also for VSB control strategies and control selection compares open loop and closed loop VSB control methods. Open loop scheduling is commonly used but does not react to real-time changes. Closed loop control offers better performance by adjusting vane positions based on actual operating conditions, but several studies highlight the importance of actuator speed and system stability. So based on that review, a lead lag compensator was selected because it improves transient response, increased stability margins, and provides good steady state accuracy under high gain conditions. The review also identified limitations such as hydraulic nonlinearities and linkage effects, which provide opportunities for future improvements. So, in summary, this literature review supports the use of a lead lag compensator for achieving fast, stable, and accurate VSB position control in Mitsubishi M5101J gas turbine. That's all from me.
Hi, my name is Amri. So I'm going to present about the methodology for our project. So we come with the first system overview. The system overview has the four parts, which is lead lag controller, a saturation block for actuator limits, the hydraulic actuator itself, and the VSB mechanism with encoder feedback. It's a standard loop, which is a standard closed loop, and the encoder continuously measured the actual vein angle and it feds it back so the controller can correct any error against the set point. Yeah. And next, we come for the physical diversion of the plan. So we derive the plan from the first principle and not curve fitting. The serve valve give a first order lag from the coil and flapper nozzle in inner tails. Newton's second law on the piston and load give the second first order lag. Rigid body kinematics convert the piston motion into the angle through an integrator and constant lever ratio. Multiply all these three in series give us our third order plan, which is GP equal to 64 over S times S plus 15, S plus 45. Yeah. And next we come for the lead lag controller design. The table B2 from our question that assign us a lead lag compensator under high gain constraint. The lead stage at phase near crossover, boosting phase margin and the speed up the transient response. The lead stage is a low frequency gain for accurate tracking without stealing back the phase margin. Together they solve the core conflict. High gain alone is the fast but unstable. Low gain alone is stable but slow. And the last part for my methodology part is the design process, the verified controller. We translate the overshoot and settling time limits into the ratio target of at least 0.69. Then we run a numerical loop shaping stage in MATLAB across gain, lead, and lag parameters, refining over three or iteration. The final controller gain 215.6 with those lead and lag 0 pole pairs. Passes all four table B2 requirement with the comfortable margin under 1% overshoot. Well, under a quarter second settling time and both stability margin exceed.
Hi, my name is Mohd Aziman. So today I will explain about result and discussion. So as the first part, our first slide, the first thing we checked was the step response, how fast the vane react to a command. Without any controller, the actuator alone takes about 41 seconds to settle, which is far too slow for the gas turbine. Once we add our lead lag compensator, that's dropped to just 0.22 seconds with overshoot of only 0.96%, as you can see here. Next, where the step response tells you how fast and how much overshoot you get, this board plot tells you how robust that behavior is, how much room you have before the system becomes unstable. At the gain crossover, as you can see here, frequency of 9.05 radian per second, we get a phase margin of 668 degree. At the phase crossover of 37 radian per second, the gain margin is around 17.1 decibels, both clear the 65 degree and 12 decibel requirement with room to spare. So the controllable is not just fast, it robustly stable. So our third slide, which is the root locus confirms stability diagram. At our design, the gain of 215.6, all 5 sec closed loop is sit on the left half plane. So the system is really stable. Next, we didn't arrive at this controller on the first try. By first iteration, a lead-only compensator failed on phase margin, overshoot, and settling time. By second iteration, it improved the phase margin to 61 degree, but the gain margin and low frequency tracking was still short. Only by third iteration, after adding the lead lag of to boost low frequency gain, we did pass all the 4 requirements simultaneously. I think that's all for me. Thank you.
Hi everyone, I'm Zarko from Team 10, and I'll be walking you through the conclusions and recommendations for our lead lag compensator design for the M501J gas turbine VSV actuation system. Let's begin with what we achieved. Our lead lag compensator met all 4 performance targets with considerable margin. The standout result is settling time. We achieved 0.22 seconds against a 0.8 seconds, roughly a 72% margin. Overshoot is essentially eliminated at 0.96% versus the 5% limit. In the frequency domain, we have a phase margin of 68 degrees against a 65-degree requirement, and a gain margin of 17.12 decibels against 12, both confirming robust stability. To put this into perspective, the uncompensated plan took about 41 seconds to settle, Our compensated system does it in 0.22 seconds. That's about a 99.5% improvement. These three recommendations don't invalidate the base design. They extend it towards hardware implementation. First, nonlinear validation would confirm the model still holds beyond the design point. Second, modeling linkage flexibility would expose any hidden mechanical resonance before they destabilize the loop. Third, assessing parametric uncertainty. Varying hydraulic pressure and fluid temperature would bridge the gap from simulation to fielded hardware. With these three steps, the lead lag compensator is ready to move from simulation to physical hardware. Thank you.